This video demonstrates how to get quick and precise results using the Fit7A digital load cell and the Panel X software by HBM. The 8-pin M12X1 male connectors and a compressed air connection are located at the rear of the Fit7A. In its original state, the Fit7A is airtight. Changes in ambient pressure will have an impact on the measurement signal. Fit7A comes equipped with a self-sealing compressed air connection and a coupling plug to help eliminate external impact. It's okay to connect the coupling plug to the compressed air connection if the humidity at the installation location is stable. A standard air hose with a 6 mm outside diameter should be attached at the coupling plug if the humidity at the installation location is subject to fluctuations. The open end of the hose can be routed to an environment with stable humidity, that is, a control cabinet. Installing the load cell is easy. As a first step, mount an existing adapter part as needed. Then the load conveyor is assembled. The conveyor belt, rollers, and the drive motor are often responsible for most of the interference in the weighing signal. Less interference means more accuracy and shorter weighing cycles. Ensure that the conveyor belt, rollers, and drive motor run as quietly as possible and that the entire structure is lightweight and rigid to reduce interference to a minimum. Once the base structure is assembled, the newly created weighing module can be incorporated in the Checkweigher. Once the load cell has been integrated in the Checkweigher, we will connect the voltage supply cable and the communication cable to Fit7A. Fit7A sensor electronics support communication via CAN Open, DeviceNet, Profibus, and the serial interface RS232 and RS485. We've selected the RS232 and RS485 interface in our example for easy communication via laptop and USB adapter. A command set with more than 100 read-write commands and multiple parameters each for the communication with Fit7A is provided. HBM offers the free software Panel X for use with Checkweighers, dosing applications, and for diagnostics. Follow the necessary steps for the configuration of the Checkweigher via the Panel X software. These include the configuration of sensor electronics for the real-time processing of raw signals or the setup of trigger signals and the setting of limit signals. Once we establish an electrical connection, we can start Panel X on the connected laptop or PC. First, we need to tell Panel X which interfaces are used for device connections and have it then scan for connected hardware. In our example, Panel X detects Fit7A at the RS232 interface of the USB connector. We can establish a connection with Fit7A and receive information about the connected module in the Home tab. We will now switch to the Application tab to select one of the applications, Standard, Checkweigher, or Filler. Another tab is displayed in the menu bar for each of the applications, and another display column on the tab Home. As we want to configure a Checkweigher, we will select the application Checkweigher. In the next step, we will complete a static calibration of the Checkweigher. We open the tab Adjustment and enter the weight value we want to use for calibrating our load conveyor in the field Calibration Weight. In our example, we will enter the calibration weight 5 kilograms. We will begin by clicking Reset to remove all previous calibration settings and then Start Calibration to initiate the weight calibration. The software issues the prompt No Load on Scale, Click Measure, asking us to remove any loads from the load conveyor. We're then prompted to click Measure 0 to calibrate the zero weight of the conveyor. We'll do just that, and a message Calibration Weight on Scale, Click Measure will appear, prompting us to enter the calibration weight on the conveyor. We are then asked to click Measure Weight to communicate the measured value of the calibration weight to the sensor array. Following the instructions step by step, we can see that a value very close to the calibration weight is displayed in the Panel X weight indicator. The static calibration process is complete. We recommend documenting the intrinsic noise and the ambient noise for the Checkweigher. A step-by-step commissioning of systems and machines in the vicinity of the Checkweigher will help identify the system or machine contributing to the noise signal. The noise signal can also be accessed later for comparisons if you notice changes in the noise behavior. An example of this might be because more machines or system components are installed in the vicinity of the Checkweigher. We want to document the noise, so let's switch to the tab Filter in our Checkweigher and ensure that all electronic filters of the FIT 7A are disabled. We will now open the Scope tab and select one of the three modes for Scope. We've selected the real-time mode for our example. We start the noise measurement and stop after an appropriate length of time. Selecting the analysis mode would have the advantage that the signal is recorded for a selectable, fixed time interval and that a frequency spectrum will also be determined. A frequency spectrum offers additional information about the cause of the noise. The Checkweigher and other possible sources of noise should be switched off for the noise measurement. Sources of noise and interference in the vicinity could be systems or machines whose mechanical vibrations are transferred onto the Checkweigher or electromagnetic couplings via insufficiently shielded cables that cause scattering. Air currents could also result in the distortion of measured values. Once you save the data, you can access it again at any time via Panel X. That will allow you to implement constructive improvements and/or detect any errors when setting up the Checkweigher. You can now activate the drive belt of the Checkweigher and repeat the above steps to get an idea of the intrinsic noise of the Checkweigher. You can also activate more system components step by step and verify their contribution to the noise and interference behavior of the Checkweigher. Let's have a quick look at the high-performance analysis function of the Panel X software before we start with the setup of FIT 7A. The analysis screen is your most important tool for optimizing the measurement signals of your Checkweigher. This screen allows the unfiltered recording of up to 13.4 seconds at a full 600 measurements per second. The software offers a variety of filters that can be configured to simulate the final filtered signal. The analysis screen offers various functions for finding the correct filter. The analysis screen is divided into three separate areas. In the top part of the screen, we can see the raw signal in black and the filtered signal in green. The lower part of the screen shows the frequency spectrum of the recording, i.e. it shows which frequency is recorded at which signal strength. Here, the black curve represents the original signal and the violet curve represents the filtered result. We can set filters, show various signals, and implement various settings for the curve display in the column on the right. All screen areas can be moved by clicking and dragging the blue separator bars. Clicking the orange button in the middle of the bars will hide the screen below or to the right. The horizontal axis at the top of the screen represents the timeline, and the vertical axis shows the measurement signal in the selected unit of measurement. The view can be moved along the selected axis by clicking and dragging the axis name. All axes have green drag points on both ends. The scale of the axes can be modified by clicking and dragging these drag points. The same applies to the lower screen reflecting the frequency spectrum. You therefore have the option of generating more detailed views of the frequency ranges. Returning to the original view is easy. Simply click and drag the current screen to the left. A zoom box can be opened for a more detailed view of the measurement signal. Simply click and drag to the right. The scaling of the two axes corresponds to the area marked by the zoom box. Even the smallest plateau deviation can be enlarged and displayed in detail using a flat zoom box. The labeling of the axes in this enlarged view will provide information about the actual magnitude of the deviation. The scaling of the axes can be expanded all the way to the maximum resolution of the load cell, which is denoted by fixed signal increments. In our example, we can see by the axis label that the deviation, which is clearly visible here, actually amounts to less than 1 gram. The column on the right provides options for detailed view settings and toggling between a light and traditional dark view style. Various input signals and triggers can be visualized in the tab Signals. Clicking the signal color allows the allocation of a color of your choice to the relevant signal. Once we have completed the static calibration and have documented the noise and interference behavior, we will then begin with the electronic processing of the raw signals from the weight measurement to adapt the overall mechanical construction to the specific product to be weighed. While the intrinsic frequency of our FIT-7A and the mechanical construction of the Checkweigher is responsible for the maximum achievable throughput rate of products to be weighed, the electronic processing of the data guarantees precision in terms of weighing. A higher intrinsic frequency allows more speed, and better electronic processing will ensure more accuracy. We'll move on to calibrating the Checkweigher. First, we do a few test measurements with a single product to be weighed and record the raw signal using the Panel X software. This test data is used for an initial optimization of the electronic processing in Panel X, and the resulting settings will then be forwarded to the sensor array of the FIT-7A. That means that in the future, the processing of the raw data can be done in real time by the FIT-7A electronic system. We will now switch back to the scope view and select the analysis mode. Then we will increase the number of data points for analysis. The number of data points defines the length of time available for doing the test measurements using the test weight. We allow the test weight to pass over the load conveyor several times. When the weighing procedure is complete, the system will display the timeline of the raw signal in the scope view. Typically, the raw signal will contain a lot of noise and numerous interferences. The overshoot of the mechanical spring element of the FIT-7A can be seen clearly as soon as the test weight is on the load conveyor. We will now begin optimizing the electronic processing of the raw signal. The electronic array of the FIT-7A includes several electronic filters, which can be adapted to the mechanical structure, the product to be weighed, and the relevant environment. These filter settings are mapped in Panel X and can be optimized to suppress noise and interference on the basis of the test measurement data. The filter settings determined here are then forwarded to FIT-7A. Multiple filter settings can be stored on a laptop, which allows you to switch between the various settings as needed. A suitable low-pass filter is selected first. There are several filter modes available for the selection of the low-pass filter. Filter mode 5 has proven to be useful for Checkweigher applications because it's a fast FIR filter. Panel X will also calculate the frequency spectrum of the raw signal for us. The frequency spectrum may help in the detection of interfering frequency in the immediate vicinity of the Checkweigher. Frequencies above 5 to 10 Hz typically do not contribute to the useful signal and only produce noise. As a first step, we will reduce these frequency portions to a level below -100 dB, meaning we will set the associated cutoff frequency of the low-pass filter to the lowest permissible value. That value is 0.125 Hz. We can see right away in the displayed frequency spectrum that the higher frequency portions are suppressed significantly. The raw signal is shown in gray and the filtered signal is shown in green or magenta in the temporal visualization and in the signal spectrum. We can also see that the signal in the temporal visualization contains a lot less noise and interference. The overall objective is to achieve a plateau as level as possible for those ranges in which the product to be weighed remains on the load conveyor. The FIT-7A sensor electronics array offers an arithmetic mean filter and 2 notch filters in addition to the low-pass filter for signal processing. While the arithmetic mean filter forms mean values across several measuring points, the notch filters suppress interference signals which are displayed as narrow peaks in the frequency spectrum of the signal. Our Checkweigher displays hardly any narrowband interference. We can use the arithmetic mean and the 2 notch filters to further improve the effect of the low-pass filter. We see that despite the configured low-pass filter, not all spectral components above 5 to 10 Hz can be suppressed to a value below 100 dB. At 12 to 13 Hz, we have reached a signal level of around -100 dB. We then dial the cutoff frequency of the arithmetic mean filter to 12.25 Hz. It will then have a similar effect as a second low-pass filter. After applying the arithmetic mean filter, we can see another significant improvement of the signal quality. At this point, we may have to zoom in to the plateau of the temporal signal to see any measure of a remaining inaccuracy. The maximum frequency, which contributes with more than -100 dB to the signal, has shifted to the significantly lower frequencies in the spectrum as well. In other words, interfering spectral components or spectral components that do not contribute to the useful signal will be suppressed. The two-notch filters can be applied the same way as the arithmetic mean filter. They suppress frequency ranges of around ±2 Hz by the specified filter frequency. Next, we will dial a filter frequency that is about 2 Hz lower than the maximum frequency, contributing -100 dB to the signal. The processed signal will once again improve significantly after the filters are applied, and our resulting plateau levels out even more. We have found very good values for the processing of our raw signal and will transfer these to the electronic array of our FIT7A. In the next step, we will have to decide which area of our plateau we will use as the basis for our weight determination. We can then specify that area for FIT7A in terms of a triggering reference signal, a so-called trigger. The triggering condition can be the exceedance of a specified measured value, and it can also be an external signal, such as from a light barrier. We will use a light barrier for the purpose of this example. The light barrier triggers as soon as the product to be weighed reaches the load conveyor, and the signal is forwarded to the input of the FIT7A. The trigger signal from the light barrier or a level trigger can be viewed under Scope in Panel X. We will now specify the time period on the plateau to be used for determining the weight and the time interval between receipt of the trigger signal and the start of the weight determination. We can see that a very level plateau is available for 60 milliseconds. That is the time we use for our measurements. The point in time at which the weighing can commence is around 370 to 380 milliseconds after the trigger signal is received. We will now move to the tab Checkweigher in Panel X. In the field Trigger Mode, we select the option External Pre-Trigger as a triggering reference signal to match our chosen structure. We copy the values for the start of the weighing process after the trigger signal was received, i.e. 370 milliseconds, and the time interval for weighing, i.e. 60 milliseconds, into the relevant fields Settling Time and Measuring Time. We will now forward these settings to the electronic array of the FIT7A and can then begin our test measurements. We will run the same package 20 times over the Checkweigher to test our settings. During the test, the weight of our product remains the same. The captured deviations will allow us to determine how accurate our weight measurements really are, taken with the settings we configured. After 20 test measurements, we can see the arithmetic mean value of the captured weights is around the expected 525.1 grams. The standard deviation is only 0.1 gram. If we compare this 0.1 gram standard deviation with the 20,000 gram maximum capacity of the FIT7A used here, then the calculation result is a standard deviation of only 50 ppm or 0.005% of the full-scale value. A high accuracy like this can be easily achieved with the right components for the load conveyor, a FIT7A, and with cleverly configured filters. After our tests, we now know FIT7A is ready for operation. The load cell can now be connected to the controller of the Checkweigher via the selected bus system or the 4 switch outputs. In the simplest scenario, a controller can be foregone altogether, and the 4 FIT7A outputs can be used instead to control expulsion devices like pushers, track switches, or uploading belts. FIT7A is therefore perfectly capable to independently select and expel bad products from serial production runs. Whichever option you choose, as the core part of your Checkweigher, FIT7A comes equipped with everything you need to ensure the success of your product.